The output impedance of a transmitter, let's say this is the transmitter that we are looking at. The output impedance of the transmitter, ZT, is 150 plus J75. So 150 plus J75. So it's inductive in nature, plus J75. So design a L-type matching network. L-type matching network. So since it looks like an L, this looks like in the shape of an L, it's called as an L-type matching network. Show that the maximum power is delivered to the antenna such that the maximum power delivered to the antenna whose input impedance is ZA, that of the antenna is 75 plus J15. That means you have a Z antenna which is 75 plus J15 ohms. If I were to directly connect it without this block in between, certainly there is a mismatch. This guy is not the same as this guy, or neither is he a conjugate. So definitely it's a mismatch. So there has to be a so-called impedance matching network. It's going to transform the antenna impedance to be the conjugate of ZT. ZA is going to be the conjugate of ZT. Alternatively, as you can see here, this condition, Zin is the conjugate of Z star, is the same as saying Zs is the conjugate of Zin 1 star. Either way, it's the same. It's just that the real parts are the same. The imaginary part, if one is the plus, the other should be a minus. So on that note, whatever that you're looking at here, whatever ZT that you have here, this L network is going to transform that to appear as Zm, so that on this plane, my Zm is the conjugate of Za. So that's what the matching network does. So for maximum power transfer, which is called as a conjugate matching, my Zm, as I see from here, should be the conjugate of Za. So then I can go ahead and decide what should be my inductance and what should be my capacitance. You can equivalently write this as, this is going to be my ZT. Then I have my C2 here. Then I have my inductor L1 here. And this whole thing is being connected to an antenna, which is represented as ZA. Let's say this is represented as ZA. So what you see from this side is ZA, and what you see from this side is Zm. This Zm must be the conjugate of Za, or alternatively, Za should be the conjugate of Zm. Both mean the same. So how do I find what is Zm now? Zm is Zt in parallel with the capacitance, which is 1 over j omega C2. Capacitance, once you see, this is going to be, the impedance is 1 over j omega C2. Then you have a series inductance. The two are in series with an inductance with this j omega L1. So that's what you write here. The Zm is Zt parallel 1 over j omega C2. Well, I just call this as C and L instead of C2 and L1. So this is C and this is L. And that two parallel are in series with my inductor. So plus j omega L. So you have this j omega all over the place. You want to do it so that it all comes to the numerator, so that you can separate out the real part and the imaginary part. And when you do that, after a tedious process, you end up getting a real part and a nice imaginary part. And this real part should be the same as the real part of antenna, but the imaginary part should be negative of the imaginary part of the antenna, because it's a conjugate of Za star, which is 75 minus J15 ohms. So this means this real part must be 75 and this imaginary part must be 15. I have two unknowns. What are they? C and L. Those are the two design variables I got. Two unknowns. I have two equations, so I can go and solve uniquely what is L and C. Of course, it will be a bit tedious, but that can be done. So if you solve for it, you get C to be 0.73 picohenry and L 6.1 nanohenry. So this is just an illustrative example. Just an illustrative example to see how tedious this method can be if you were to do by hand, if you were to do it by hand, by calculation, because but the alternate way is to do it with what is called as a Smith chart.